Once again, the valence electrons sit in the yellow area, that's the valence band, and the red area above is the conduction band. The gap between them is what we call the band gap. For instance, in conductors, the band gap is basically zero. As you can see here, the valence band and the conduction band actually overlap. So electrons in the valence band are already in the conduction band. There is no gap to cross, which means the outermost electrons are free to move and conduct electricity right away. Now, in insulators, the band gap is very large. That means there are almost no free electrons available to carry current. In other words, the electrons in the valence band don't have enough energy to jump into the conduction band. Since they cannot make that jump, so they simply stay stuck, and that's why insulators do not conduct electricity. While in semiconductors, things are different. The band gap is much smaller, so electrons only need a little bit of energy to make the jump from the valence band to the conduction band. This energy can come from heat. Even just slightly above absolute zero can be enough. Take silicon for example. It has a band gap of about 1.1 electron volts. With a little thermal energy, some electrons can gain enough energy to jump into the conduction band. Once they are there, they are free to move, and if we apply a voltage or electric field, they can carry current. Now you might be wondering, where do wide band gap semiconductor fit into all of this? Well, wide band gap materials simply have a larger band gap than traditional semiconductors like silicon. For example, silicon carbide has a band gap of around 3.3 electron volts, and gallium nitride is slightly higher with a band gap of about 3.4 electron volts. So compared to silicons of 1.1 electron volts, that's a big jump, and it opens up some major advantages, like that wide band gap materials can handle higher voltages without breaking down, making them ideal for high power applications. They lose less energy as heat, which improve energy efficiency in power electronics. And because of their wider band gap, these materials can operate at much higher temperatures without degrading. Also, wide band gap devices like SiC and GaN can switch on and off much faster, which means we can run things at higher frequencies and make the design smaller and more efficient with less cooling requirements.